Hello, this is Brian Siefker with my final presentation for my optimization project, surge arrestor support brackets for power transformers. The optimization program runs using the Microsoft Excel solver. In order to run, the user will fill out his arrestor mass, any information on special loads, and the size requirements for the design. The designer can also change with these values here, but in general he will not. This costing is an approximate value. It's not the values we actually use. Due to intellectual security, I had to change them, but they are in the ballpark. Once this information is filled out, the user will hit solve, and it will solve this value by making sure all these constraints are less than 0. Once it is run, the solver has selected the optimum size main support and cross support that satisfy all constraints and gives you the minimum cost for the design. Pressing the solve button runs a macro that first sets both the selections to 1, the smallest possible value, and then runs the solver that has been preset up inside of Excel. Here is a snapshot of the solver workbox. The solver attempts to minimize the total cost by changing the size of the cross support and main support. The constraints on this are that both of the main support and cross support selections must be integers, and they must be between the allowed values, 1 to 7 for the cross support, 1 to 11 for the main support. It then also seeks to make sure that all the other constraints are less than or equal to 0. Those are the yield constraints and the deflection constraints. The solver in Excel can run with a nonlinear, a linear, or an evolutionary program. For this program, because of the discrete values required to solve, I could only get the evolutionary program to run with good answers. The other constraints in the solver are based on the ASCE guide for building design. In transformers, for the surge arrestors, we're worried about dead, ice, earthquake, wind, and wind on ice. In order to best suit those, the 4 equations that are required are equation 1, equation 5, and equation 4. Equation 4 has a variant that takes into account atmospheric icing. As the solver runs, it solves for both the stress and deflection on each of the beam for each of the 4 different combinations. Although it is selected as an evolutionary optimizer, based on the small options we have to choose from, it really runs as more of a brute force calculation, checking each of these and figuring out which is the lowest cost. As it changes each one of these, this calls a lookup table from a different page on the Excel that grabs all the values needed to check the loading and calculate the deflections and the yields. Any of the combinations that pass are then considered, and the lowest cost option is output. Here is one example of an output. As you can see, all the cells are green because all of the constraints are less than 0. And just to show what happens, here is a list of some standard examples I ran, from small to very large, with all natural occurrences happening to it. In all cases, the I-beam was the cheapest option. So that is by far the easiest solution. We will always use I-beams. However, channels and tubes were both selected, depending upon the size. For smaller designs, channels were the most cost-effective. On larger designs, the channels were not strong enough. However, since so many of our designs are in the smaller range with no seismic, the recommendation for the cross supports is that both be considered, with channel being first, and if it doesn't meet, then using a tube where necessary.